Hey, how are you doing on the energy chapter in physics?
I think there's some things I need to work on. I get the idea of potential and kinetic energy, but I'm still confused on how they are related in conservation of energy.
Yeah, I don't know how to decide when it's conserved and when it's not. I am confused because I thought energy was always conserved.
It is always conserved, and I was confused too, but I finally understood when energy becomes thermal or sound energy, it is not conserved in that system.
Well, what about when energy is transferred from one object to another?
What do you mean?
Well, aren't things gaining and losing energy all the time?
Right. But all the energy that is lost from one system is gained by another. It never disappears, so we can keep track of every little bit of it.
But don't we have problems where we say energy is lost?
Oh, those cases are where energy leaves the system that we're interested in, but it doesn't just disappear.
That makes sense. But when we're solving a problem, how can I know if energy is conserved in the system or not? Is it lost when the problem states that there is friction?
Yes, or air resistance or something like that. Another hint is when the problem describes a collision between two objects as elastic or inelastic.
So energy is conserved when it's elastic, right?
Right. If it's elastic, it means energy is conserved.
Do you want to try out one of the homework problems with me? Let's do a challenge problem.
Sure, two heads are better than one.
A 200-gram steel ball hangs on a 1-meter long string, creating a pendulum. The ball is pulled sideways so that the string is at a 45-degree angle, then released. At the very bottom of its swings, the ball strikes a 500-gram steel paperweight that is resting on a frictionless table and undergoes a perfectly elastic collision. To what height does the ball rebound?
I remember the professor saying we should break up complex problems, so maybe we can draw several pictures. So the weight is on the floor and a pendulum will hit the weight like this. Where's the 45-degree angle?
Okay, so I think it's the one right here.
Do we have all the information we need right now?
Yeah, I think so. So now I think we just need to figure out if energy is conserved in this collision.
I think it is because the problem said it was a perfectly elastic collision.
Alright, so let's figure out the initial energy of the system. We have to account for energy in both the pendulum and the weight, right?
Yes, and the pendulum has gravitational potential energy, but I don't think it has any kinetic energy because it's at rest. And the weight has no potential or kinetic energy because it's just sitting at the table.
Okay, so the initial energy of the system is just the gravitational potential of the pendulum. Should we calculate that?
I think we should wait until the end to calculate. Maybe something will cancel out and make calculations easier.
Let's figure out the energy after the collision. The pendulum will achieve some maximum height. So at that point, the pendulum will only have gravitational potential energy.
But won't it be moving after the collision?
Yes, but I am thinking of the pendulum when it has a new maximum height.
Oh, okay.
And the weight will only have kinetic energy because it will still have no gravitation potential energy.
I get it. So our final energy is the kinetic energy of the weight and the potential energy of the pendulum. Since energy is conserved, the final and initial energies should be equal to each other.
So the initial energy of the system is just the gravitational potential of the pendulum, which is the mass of the pendulum, times the gravity times the initial height above the table.
And the final energy is the kinetic energy of the weight, 1/2 mass times velocity squared, plus the gravitational potential energy of the pendulum, mass times gravity times the final height.
But we don't know the initial height of the pendulum, the speed of the weight after the collision, nor the final height of the pendulum. There is no way we could solve this equation without more information.
Now what?
I think we use trig to find the initial height of the pendulum. Look, it makes a triangle. So L times cosine theta gives us this distance.
So the initial height is L minus this distance D?
Yes. Alright, so let's calculate the initial height. I get 0.293 meters.
Okay, but what's the next step? How do we find the speed of the weight after the collision?
Actually, I'm not too sure.
Wait, how about those equations in the book that are specific for elastic collisions? You know, the ones that relate the speeds of two objects before and after they collide? I think they combine conservation of energy and conservation of momentum.
Yes, let's use those. Oh no, we're still missing another variable. We don't know the velocity of the pendulum before the collision.
I think we should be able to use conservation of energy again, but this time between the pendulum at its initial position until right before the collision.
I don't know.
Okay, why don't we recap first?
I think that would be best. I'm feeling a bit lost now.
We started with conservation of energy between the start of the pendulum's motion and the time when it rebounded to its max height after the collision. But we realized we couldn't find the final height of the pendulum because we still didn't know the speed of the weight after the collision or the initial height of the pendulum. We then realized that we could find the initial height of the pendulum with a little trig. Now, using the elastic collisions equations you just found, we can probably find the speed of the weight and plug it back into the first equation.
Alright, but we still don't know the speed of the pendulum just before the collision.
Calm down, I think we're almost there. How about using conservation of energy between the start of the pendulum's motion and the moment just before it collides with the weight? I think it will give us the VIA in these equations.
Okay, well, we already know the energy right at the start. It's the gravitational potential energy of the pendulum. So just before the collision, the pendulum is moving fast because all its energy was transformed into kinetic energy. The masses cancel out and we have that the speed is square root of 2 times gravity times the initial height. Plugging them in, I get 2.4 meters per second.
See, you could do it. Now we do not have any more unknowns.
Thanks. Now let's finish the beast. We must use the second elastic collision equation to find the speed of the weight.
Wait, why do we have to use the second equation?
Because in these equations, A is the pendulum, the object initially moving, and B is the weight.
Oh, okay, you're right.
So, using the second equation, I get 1.37 meters per second. Yay, finally! Now we can find the final height by plugging everything we know into the main conservation of energy equation. I get 0.0541 meters.
Which makes sense. It is smaller than the initial height. I am so happy to be finally done with this problem.
Me too. Thank you for working through this problem with me.